Okay, so today we're talking about the ideal gas law. Okay, now the ideal gas law is sort of a culmination. It's like all of the gas laws in one, which I know is the combined gas law is here, but there's actually one more thing we need to talk about, which is something that we haven't really covered yet in this unit, but we have actually covered it before. So I'm going to kind of use an example for this. So there are factors that affect how a gas behaves. Now, the three we focused on: temperature, pressure, and volume. We focused on them pretty hard over the last week or so. But there's one more factor at play here. And to do this, here's an example. This is a soccer ball. And the soccer ball goes from deflated to inflated. Now, it's not because we increase the temperature, it's not because we increase the pressure, and it's not because we change the volume. Like, what is causing that volume change? The volume does change. But what the difference here, that fourth factor, is how much air there is. So all of the gas laws, Boyle's law, Gay-Lussac's law, Charles' law, combined gas law, they all are about making sure you have the same amount of gas. But the amount of gas can change, so that can be a factor here. That's where the ideal gas law comes in. Okay? So we have actually talked about the amount of gas before when we did stoichiometry. So this idea of how much gas you have was first proposed by Amedeo Avogadro. He's got a really long, complicated name. We just call him Amedeo Avogadro. It's pronounced, I think, Lorenzo Romano Amedeo Carlo Avogadro, Conte de Corregla y Cerreto. Probably didn't pronounce that right. But so what he discovered is that equal volumes of gases, meaning the same size, if they're at the same temperature and at the same pressure, they're going to contain the same number of molecules in them. So if we have three balloons and they're all the same size, and they're all at the same temperature, and they're all at the same pressure, all three balloons have the same number of molecules inside them, no matter what that is. And we use this in stoichiometry. That was a mole equals 22.4 liters at standard temperature and pressure, STP. So when we used this before, it was, this is what a mole is. If it's this volume and this temperature and this pressure. So all four things: how much we have, what the volume is, what the temperature is, what the pressure is. Standard temperature and pressure was 0 degrees Celsius and 1 atmosphere of pressure. That's like the standard. And so it was, if we had 22.4 liters of it, we knew we had a mole. Okay, if we had any other amount, we could actually figure out how much we had by using stoichiometry there. But that was always same temperature and same pressure, 0 degrees Celsius, 1 atmosphere. The ideal gas law here takes into account that it could be a different pressure and it could be a different temperature. Okay, but we can still figure out how much it is if we know pressure, volume, and temperature. So here's the ideal gas law. PV equals nRT. P stands for pressure, V stands for volume, N stands for number of moles, okay, the amount. R is something called the ideal gas constant. More on that in just a minute. And then T is temperature, which of course we're going to use Kelvin. Okay, you have to use Kelvin for this. So P times V equals N times R times T. All right? Similar situation where we're going to plug in everything we know, and then we're going to figure out what we don't know. All right, so the four variables, pressure, volume, temperature, and moles are there, but we also have this thing called the ideal gas constant. This is something that we actually had to measure. It's a constant of the universe that basically makes the math work. Okay, now it's different depending on the units you use for pressure, volume, and temperature. We're always going to use Kelvin for temperature, and we're always going to use liters for volume when we use this equation. So if you get like milliliters, you're going to have to change it to liters. Okay, but pressure can be measured in either atmospheres, kilopascals, millimeters of mercury, so on and so forth. Right? So R is different based on those different pressure units. If we use atmospheres, then R is 0.0821. If we use kilopascals, R is 8.31. If we use millimeters of mercury, R is 62.4. Okay? And that's just a constant in order to make the math work. All right? Now, this equation is different from the other ones because the other ones were like P1 and T1, P2 and T2. That was describing how pressure and temperature changed, or pressure and volume changed. So you had two different pressures, two different volumes. This is just, here's the pressure, Here's the volume. Here's the temperature. How many moles is that? Okay. If it was 0 degrees Celsius and 1 atmosphere, we could use the volume to figure out how many moles that was. That was that whole 22.4 liters equals 1 mole thing. But it only works when the temperature is 0 and the pressure is 1 atmosphere. So now we're going to have a different pressure, different temperature, different volume, but we can still figure out how much we have. It's not about how it's changing, it's how much we have. Okay? So first example problem. Okay, so calculate the number of moles of gas contained in a 3.0 liter vessel at 25 degrees Celsius, which has a pressure of 1.50 atmospheres. Okay, so my equation, first off, we have PV equals nRT. Right, now coming up here, this here is the volume. This here is a pressure. This here is a temperature. Okay, and it's in Celsius. So the first thing I'm going to need to do is change that Celsius to Kelvin. All right, so I'm going to add 273 to it, and that gives me 298 Kelvin. Okay, so we have our temperature in Kelvin, we have our pressure, we have our volume. The only thing we don't have besides moles is our R value. Okay, so looking up on those things that I just had on the slide, you should have written them down in your notes. R value here, since my pressure is in atmospheres, okay, I'm going to use the R value, which has the unit of atmospheres. So that was 0.0821. And the units are liters, atmospheres, over moles, Kelvin. Okay, so this is with all of those units. And I've got liters, Kelvin, atmospheres, and I'm going to be finding moles. All right, so take all of this and plug it into the equation. So pressure is 1.50 atmospheres times the volume, which is 3.0 liters, equals number of moles, I don't know that, I'm just going to put X, times the R value, which is 0.0821 liters atmospheres over moles Kelvin, times the temperature, which is 298 Kelvin. And then you simplify. Okay. Okay, so this side would simplify to 4.5 ATM times liters. This side would simplify to 0.0821 X times 8.3738, and Kelvin here would cancel, so it would be left with liters, atmospheres over moles. Okay, now I'm going to try to get X all by itself, so I'm going to divide both sides by 8.3738. Now, the liters cancel, the atmospheres cancel, and that's divided by a mole, so we're going to end up with moles. The only thing left over here is X, so 4.5 divided by 8.3738. 0.537390. I'm already going to know I'm going to need to round that, so looking at my numbers up here, 3 sig figs, 2 sig figs, 3 sig figs, 3 sig figs, 2 is the lowest. So I'm going to round that up to 0.54 moles. Okay. Okay, so here's another example problem. Pause the video and try it yourself first. Got an answer? Okay, so the equation here, we got PV equals nRT here. Right, so my V is 2.00 liters. The pressure is 117 kilopascals. The temperature is 35 degrees Celsius, which if I add 273 to, I get 308 Kelvin. Okay, So 308 Kelvin. So I've got my pressure, temperature, and volume. My R value, the R value that I want to use, since my pressure is in kilopascals, I'm going to use the 8.31 R value. Liters, kilopascals, moles, Kelvin. Okay, so I'm going to start plugging numbers in. Pressure, 117 kilopascals, times volume, 2.00 liters, equals moles, I don't know, okay, times R value, 8.31 liters times kilopascals over moles Kelvin, times temperature, 308 Kelvin. Okay, so I'm going to find moles here, find X. First I'm going to simplify. This simplifies to 234 kilopascals liters. That's still X. (8.31 times 308 is 2,559.48. Kelvin cancels. Liters times kilopascals over moles. Okay. Next, I'm going to divide both sides by 2,559.48. So it cancels. Those cancel. The only left over here is this. This will become moles. So 234 divided by 2,559.48 is 0.0914248,207. Okay? Now, that's actually not my final answer because that tells me how many gas molecules I have, how many moles of them, but it asks actually for grams. So I actually have one more step here. Okay? It wants the weight of it. So I need the molar mass of carbon dioxide. Okay, CO2. 1 mole of CO2, carbon, oxygen, oxygen, is 44.01 grams. Okay, so I'm going to take this number here, 0.0914248,207 moles, times it by its molar mass, 1 mole over 44.01 grams. Okay. This gives me 4.023606358 grams. So that is my final answer. So that's the one I'm going to round. So I look back up here. We got 3 sig figs, 3 sig figs, 3 sig figs, and 3 sig figs. That's 4 sig figs. So 3 here. So we're going to round this to 4.02. Next one's a 3, so it rounds down grams.